Okay.
I am Ijaz Ahmed. In today's lecture, we will discuss the co-spectral graphs and we will prove a theorem on the spectra of regular graphs. So we start with the definition of what we mean by saying graphs are co-spectral. So here we have a definition. Co-spectral graphs. So we call two graphs G1, two graphs G1 and G2 are co-spectral. In fact, these two graphs should be of same order. Two graphs G1 and G2 of same order and size are said to be co-spectral or said to be co-spectral if they have the same spectrum. They have the same spectrum. That is, if spectrum of G1, that is if spectrum of G1 is equal to spectrum of G2. Or we can write this, and where the spectrum of G1 is the set of eigenvalues together with their multiplicities. So we call two graphs as co-spectral if they have the same set of eigenvalues and with the same cardinalities. Now we will take up certain examples. One obvious fact is that isomorphic graphs have the same spectrum. The first example is isomorphic graphs. Isomorphic graphs have the same spectrum, or we call this isomorphic graphs are co-spectral. And this is actually an obvious observation. This is obvious. Now, we will try to look for the non-isomorphic graphs that have the same spectrum. So our question is, does there exist non-isomorphic graphs that have the same spectrum? And the answer to this question is in affirmative. In fact, there exist the graphs that have the same spectral and there are non-isomorphic co-spectral graphs. And here we shall take the example of two non-isomorphic graphs that have the same spectrum. So this shall be our example number 2. So here we consider the graph G1 is equal to the star graph on 5 vertices, that is K1, 4. And consider a graph G2, which the union of two graphs, K1 union C4. Then these are two non-isomorphic graphs and they have the same spectrum. In fact, we will prove it. So first we will see how these two graphs are non-isomorphic. So now here this K1, 4, it is a graph of this form. It has 5 vertices and there is one vertex which is adjacent with the remaining 4 vertices. So therefore this is vertex which is adjacent here. So this is K4. Let's call the vertices as V1, V2, V3, V4, and V5. So this is our graph G1. Now here we have this G2, which is K1 union C4. So this is the graph that has one vertex as goes U1. And then we have to take its union with C4. So C4 is a cycle on 4 vertices. So it's a graph of this form. So let's call these vertices as U2, U3, U4, and U5. Now clearly we can see that these are two non-isomorphic graphs. Now we will compute the spectrum of these two graphs, and we will show that they have the same spectrum, and so they are co-spectral. Now before discussing their eigenvalues, we will recall the previous theorem that we had done in the previous lecture, and that's the Sachs theorem. So we recall Sachs theorem. So we recall Sachs theorem. We had proved that if G is a graph of order n, if G is a graph of order n with characteristic polynomial, this P G lambda, this is equal to lambda power n, E1 lambda power n minus 1, plus so on, plus En minus 1 lambda plus En. So if we have a graph G of order n with this as its characteristic polynomial, then we have the formula for computing these AIs. Then this AI is given by summation H belonging to Hi minus 1 power P of H into 2 power C of H, where Hi is the set of all basic figures. Hi is the set of all basic figures of order I in G, and this P of H denotes the number of components in H, denotes the number of components in H, and C of H denotes the number of cycle components in H. Cycle components in H. And in fact, in the previous lecture, we have also explained what we mean by these basic figures. These basic figures are the graphs which are either K2s or cycles, or the union of K2s and cycles. So this was the Sachs theorem that we proved in the previous lecture. Now, using the Sachs theorem, we will compute the characteristic polynomial of these two graphs. So they will, and we will accordingly show that they have the same spectrum. Okay, now we have this K14 equal to G1, and G2 is equal to K1 union C4. Let's call the characteristic polynomial of this G1 as P of G1, Pg1 lambda, let P G1 lambda. This is equal to, suppose this will be now lambda power 5, then plus A1 lambda power 4 plus A2 lambda power 3 plus A3 lambda square, then plus A4 lambda plus A5. And similarly, and let P G2, now let's call this as mu, be equal to mu power 5 plus suppose B1 mu power 4 plus B2 mu power 3 B3 mu square plus B4 mu plus B5. Now suppose these are the characteristic polynomials of these two graphs G1 and G2, then by Sachs theorem, this A1 is equal to 0, and in fact B1 is also equal to 0, because this AI, its formula is like this. Its formula is the summation over -1 power P of H, 2 power C of H, where the summation runs over all basic figures of order I, and the basic figure is a graph which is either K2 or a cycle or the union of K2s and cycles. So now when we compute this A1, it means the set of all basic figures which consist of one vertices, but a basic figure is at least K2, so therefore there is no basic figure of order 1, so therefore this A1 is always 0 and B1 is always 0. And in fact, from the adjacency matrices, we already know that this A1 is the set of, this A1 is defined to be the trace of the adjacency matrix, and we know that the trace of the adjacency matrix of any graph, whether it is connected or disconnected, is always equal to 0. So A1 is 0 and B1 is 0, but this can also be seen from the Sachs theorem. Okay, now then A2 and B2. Now A2 is again the summation in this H contained in H2 -1 power P of H. So let's write it again here. So now this A2 will be equal to summation H belonging to H2, then -1 power P of H into 2 power C of H. Now here we have to choose this H as a component, as a component in H2, where H2 is the set of all basic figures of order 2. So therefore this H2 will contain the edges of G1, because this A2 is being computed from G1, so therefore this H2 will consist of all the edges of G1. So therefore the summation will run over the edges of G1. And in fact, whenever we choose this H contained in H2, H is a single element of H2. So therefore this P of H will always be equal to 1, because we will always choose a single H, and the number of cycle components in H will always be equal to 0. So therefore the sum will contain as many terms as the number of edges in G1. So in fact, G1 has 5 edges. Sorry, G1 has 4 edges. So therefore the sum will contain 4 entries, and each entry will be of this form. So therefore this will be of the form -1 power 1 into 2 power 0. Then again, -1 power 1 into 2 power 0, -1 power 1 into 2 power 0, plus -1 power 1 into 2 power 0. And this -1 power 1 is -1 is here, and H is chosen as a single edge of G1, and so therefore that H contains just one component and it contains no cycle component. So therefore this is equal to -4. So therefore A2 is equal to -4. And similarly we can see that, so therefore actually this A2 is the number of edges of G1, and similarly B2 is the number of edges of G2. Similarly B2 is equal to -4, because we again know that this B2 has 4 edges. Now next we will compute, similarly we will check for what is A3. Now A3 will similarly be the number of triangles. So if we write this A3 here, okay, now again, this A3 will be equal to summation over H belonging to H3 minus 1 power P of H into 2 power C of H. So now here this H3 consists of the basic figures of containing of order 3. H3 is a list of all basic figures of order 3, but a basic figure of order 3 means a cycle of order 3, and that means it's a triangle. Now if we look at these two graphs, this graph G1 does not contain any triangle, and in fact this G2 also does not contain any triangle. So therefore, clearly this A3 is equal to 0 because G1 has no triangle. Similarly, G2 has no triangle. G2 has no triangle. Thus, B3 is equal to 0. Now again, if we want to compute A4, now again A4 will be the sum like this. It is summation H belonging to H4, then minus 1 power P of H into 2 power C of H. So now this H belonging to H4, now this H will be a basic figure of order 4. Now H4 is the list of all basic figures of order 4. And this H will be an element of this H4. So this H will contain our 4 vertices. And now the basic figures of order 4 from A4, they are either the union of 2 cycles or they are C4s. So now here we will write now basic figures of order 4 are either cycles of length 4 or either cycles of order 4 or union of 2 edges. Union of 2 non-adjacent edges. Non-adjacent edges of G1. We need non-adjacent because if we take 2 adjacent edges, then they will not form a basic figure because P3 is not a basic figure, only K2 is a basic figure, Cn is a basic figure, and the union of K2s and Cns are basic figures. So now if we look at the graph K14, it does not have any pair of edges. It does not, first it does not have a cycle. So it contains no basic figure, which is a cycle of order 4. Now, a basic figure of order 4 can also consist of 2 non-adjacent edges, but we can see in K14 that there is no pair of non-adjacent edges. So therefore, it trivially follows that. So hence, this A4 is equal to 0 because this K14 does not contain any cycle of order 4, and also it does not contain a union of 2 non-adjacent edges. And then similarly, we will compute similarly. Now again this B4. Now this is again the summation H belonging to H4 minus 1 power P of H into 2 power C of H. Now again here we have to look for this H4 from the graph G2. Now here G2, as we know that this graph G2, it is a graph consisting of this vertex U1 and a cycle of length 4. So this is U2, U3, U4, and U5. Now here we have to look for the basic figures of order 4 from this G2. Now basic figures of order 4 in G2 are: one is this basic figure of order 4. It is the cycle of length 4 which is in G2, which consists of these 4 vertices U2, U3, U4, and U5. So this is a basic figure of order 4. But we also have a basic figure of order 4 like this, which consists of these 2 edges, U2, U5, U3, U4. So this is also a basic figure of order 4. But we also have a basic figure of order 4 like this, which consists of these 2 non-adjacent edges, U2, U3, U5, U4. And now we can clearly see that there is no more basic figure of order 4 in this G2. So hence, this B4, now the summation will run over these 3 elements. So this summation will contain 3 entries. So first will correspond to this one. So it will be -1 power P of H. Now here this is the H for the first term. So it consists of just 1 term. So it is -1 power 1 into 2 power C of H. Now this basic figure consists of 1 cycle. So it is 2 power 1. So this is the term which corresponds to this H. Now this is also the second edge then plus. Now here this is -1 power. Now this basic figure consists of 2. This basic figure consists of 2 components. So here P of H is equal to 2. And now 2 power C of H. Now this basic figure does not contain any cycle. So we have 2 power 0. And this is the term which corresponds to this basic figure, then plus. And similarly here we will obtain -1 power 2 into 2 power 0. And we can clearly see that the first term is equal to -2, the second term is equal to +1, and the third term is also equal to +1. So this is equal to 0. Therefore, this B4 is equal to 0. And lastly, this B5 is also equal to 0, and A5 is also equal to 0. The details here are left as an exercise. Details left as an exercise. So therefore, what we conclude from these 2 graphs G1 and G2, so with thus we have the characteristic polynomial of G1 in lambda. This is equal to lambda power 5 minus 4 lambda cube. And the characteristic polynomial of G2 in mu. This is again equal to mu power 5 minus 4 mu power 3. So therefore, these 2 graphs G1 and G2 have the same characteristic polynomial because we computed the values of A1 is 0, B1 is 0, A2 was -4, B2 was -4, and all the remaining coefficients are equal to 0. So these are the 2 characteristic polynomials. In fact, they are same. So they have the same set of eigenvalues. So we can solve these equations. So that's the spectrum, or the spectrum of G1 is equal to spectrum of G2, and this is equal to now 0 is a root 3 times. So it is 0 is a root 3 times, 2 is a root 1 times, and -2 is also a root once. So this is the spectrum of G1 as well as G2. So in fact, this is the smallest pair of graphs which are non-isomorphic but co-spectral. So here we have a note. This G1 is equal to K14 and G2 is equal to K1 union C4 is the smallest pair of graphs the smallest pair of graphs that are co-spectral. So this was one example. We shall in fact take one more example of the co-spectral graphs. Now example number 2 is example number 2. In fact, this is the smallest pair of connected graphs, pair of connected non-isomorphic graphs. Non-isomorphic graphs which are co-spectral is so this pair is G1. This is the graph of this forum. We construct this graph like this. Okay, so this is our G1. Now we will construct G2 here. This G2 is a graph of this forum. So we have an edge here and an edge here. Sorry, this is not like this. We have an edge which connects these two vertices, and then we have these two edges. Now we can see that these are the two graphs that have the same order, and in fact the number of vertices is equal to 6. And they both have the same number of edges. The number of edges is equal to, so there are 7 edges in both of these graphs. So they have the same order and the same size. And in fact, these two graphs are non-isomorphic. And that can be clearly seen from one of the properties, like this has one pendant vertex, but this has 2 pendant vertices. This has a vertex of degree 5, but this has no vertex of degree 5. And similarly, we can find out other properties of these two graphs to conclude that they are not isomorphic. But these two graphs have the same characteristic polynomial, which can again be seen from the Sachs theorem. And the characteristic polynomial of these two graphs is given by the characteristic polynomial of G1 and G2 is given as this x power 6. Sorry, yes, they are the graphs of order 6. So this x power 6 minus 7 x power 4 minus 4x cubed plus 7x squared plus 4x minus 1. This is the characteristic polynomial of G1 as well as of G2. So therefore, they have the same spectrum. Okay, now we come to the theorem for the regular graphs. In fact, as in general, there is no special relationship between the structure of a graph and its spectrum. Or if we are given the spectrum of a graph, then we cannot say in general, we cannot say anything about the connectivity of a graph, and we cannot say about anything about the structure of a graph. So as such, the spectrum of a graph does not tell us anything about the connectivity of a graph. But for the regular graphs, we have a relationship between, we have a nice relationship between the connectivity of a graph and its spectrum. So here we come to the regular graphs now. So before taking up a theorem, we will define what we mean by a regular graph. So a graph is said to be regular. A graph G is said to be k-regular, said to be k-regular if every vertex of G, has degree k. Now we shall write this a line or two as such. The spectrum of graph does not convey anything about the connectivity, of the graph. But however, the following theorem gives a relation between the connectivity of a regular graph, between the connectivity of a regular graph and its spectrum. Okay, so now we shall state this theorem. Let G be a k-regular connected graph let G be a k-regular connected graph, then this k is an eigenvalue of G. Then k is an eigenvalue of G with algebraic multiplicity equal to 1, with algebraic multiplicity equal to 1, and eigenvector this 1, so on, 1 transpose. Also for every eigenvalue, lambda of this G, we have this mod of lambda is less or equal to K. So therefore, for a K regular connected graph, K is an eigenvalue exactly once, and the corresponding eigenvector is this, the n tuple of ones. And for all the eigenvalues of this K regular connected graph G, this mod of lambda is always less or equal to K. That means all the eigenvalues are bounded by K. Now we shall come to the proof of this theorem. Proof. So let A be the adjacency matrix let A be the adjacency matrix of G, then each row sums to K, and each column also sums to K, and each column sums to K. As we know from the definition of the adjacency matrix, the sum of the number of ones in a row or a column represents the degree of a vertex. Now, since the underlying graph G is a K regular graph, so all the vertices have degree K. That means each row will contain exactly K ones, and each column also contains exactly K ones. So therefore, each row sum is equal to K and each column sum is equal to K. But from matrix theory, we know that if in a matrix the row sum and the column sum is equals some particular number, then that scalar is always an eigenvalue. Now each row sum and column sum is equal to K, so thus K is an eigenvalue. Thus K is an eigenvalue of G. Now we will show that this vector U, which is the n tuple of ones, we will show that it is the eigenvector corresponding to K. So now let U be equal to this 1, 1, so on, 1 transpose. Then we will compute A times U. While A is the adjacency matrix of G, then this A times U is equal to A times this vector 1, 1, so on, up to 1. Now here, when we multiply the first row of A with this n tuple, with this n tuple of ones, then we will actually here the answer will be a column vector. So when we multiply the first row of A, where A is the adjacency matrix of G with this column vector, then clearly we will get K here, because this first row of A will consist of K non-zero entries, and each non-zero entry is equal to 1, and the remaining entries are equal to 0. And similarly, the second row also has exactly K non-zero entries and K non-zero ones actually. So if we multiply the second row of A with this column vector, we will again get K. And similarly, each last row, the nth row of A, when multiplied with this vector, will again give us K, because all the vertices have degree K. So we have this vector here. Now we can take K outside of this matrix. This is equal to 1, 1, so on, up to 1. So that is what we obtain. That is, we have AU is equal to K times U. And this equation clearly tells us that this u is an eigenvector corresponding to the eigenvalue u. So thus eigenvalue k. Thus u is an eigenvector, or we will just write that this u lambda is an eigenpair of A. This is an eigenpair of A, where eigenpair means that this u is an eigenvector and lambda is the corresponding eigenvalue. So we are done with proving that lambda is an eigenvalue and this n tuple of ones is the corresponding eigenvector. Now we will show that this eigenvalue u has algebraic multiplicity equal to 1. Okay, so how we will do that? So now let's try to consider. Now let suppose x is equal to x1, x2, so on, xn transpose be an eigenvector. Suppose this is an eigenvector corresponding to lambda, corresponding to k, corresponding to eigenvalue k. Then what we have, then this ax will be equal to k times x, because this is the definition of an eigenvalue as an eigenvector. And let xj be the entry in x with largest absolute value, with largest absolute value. Okay. Now similarly, again, let this aj denote the jth row of A. Denote the jth row of the matrix A, where A is the adjacency matrix of G and G is a K regular graph. Then as we have, then from AX is equal to KX, we have this, when we multiply the jth row of A with X, we will get K times XJ. So that is this. Now this AJX, this means the, now this AJX means the sum of elements in this X, sum of those elements in X which correspond, which are multiplied with the non-zero entry, the jth row of A. Now we know that this jth row of A contains exactly k non-zero entries, and each of those non-zero entries are equal to 1. So this AJX means the summation over xi, where the sum runs over all vertices vi, which are adjacent with the vertex vj. So therefore, that is, we have this summation, that's we have the summation I in fact, this is I running from 1 to n first, then xi, and this is equal to k times xj. But now here, so actually we don't have the sum running from I to xi, I from 1 to n. So this is summation over xi is equal to k times xj, where I runs over those vi's, where vi is a vertex of j. This I runs over those vi's which are adjacent with Vj, which are adjacent with Vj. Because here we need, when we multiply this Aj with the column vector x, then we will have a non-zero entry xi if that ith vertex is adjacent with the jth vertex, because here on the right hand side we have xj. So thus we can write, thus we have, thus we have the summation ixi. Now this summation will have exactly k non-zero terms. So let those non-zero terms be, suppose xi1 plus xi2 plus so on plus xik. And now the right hand side is k times xj. So therefore this should be equal to xj plus xj plus so on plus xj, and this sum is k times. But now here we have assumed that this xj, it is an entry in X with a maximum modulus. So when we have this xj is the entry, the maximum modulus, that means that the modulus of these xi1, xi2, xik is always less or equal to k. So none of these xij's can have their modulus less than k, and in fact none of them can have modulus greater than k. Because if some of them have modulus greater than k, that would be contradiction to the fact that xj has the largest modulus. And similarly, if some of these xi's has smaller modulus than xj, then it will imply that some other xk has a bigger modulus than xj. So therefore, all of these xi1, xi2, and xik, they must be equal to xj. So therefore, what we have, so hence we have, since xj has the largest modulus, since xj has the largest modulus, in x, thus this x1 is equal to x2 is equal to so on is equal to xn. In fact, they must all be equal, and suppose they are all equal to some number, let's call it alpha. So therefore, we have this x is equal to, suppose, alpha so on up to alpha transpose. So this is equal to alpha times u. So this means that if we consider any eigenvector corresponding to lambda, then that's always a scalar multiple of u. So hence, every eigenvector of lambda is a scalar multiple of u. Is a scalar multiple of u, where this u is equal to 1, 1, so on, 1 transpose. So what does this mean? This means geometric multiplicity. This means geometric multiplicity, that is gm of lambda, is equal to 1. But we know that geometric multiplicity is less or equal to algebraic multiplicity. But here we have one more nice fact. But since A is symmetric, since A is a symmetric matrix, and since each symmetric matrix is diagonalizable, and each symmetric matrix is, in fact, symmetric matrices are orthogonally diagonalizable and each symmetric matrix is diagonalizable. So the arithmetic multiplicity of, arithmetic multiplicity and geometric multiplicities are always equal for symmetric matrices. So AM is equal to GM. So algebraic multiplicity of every eigenvalue of a symmetric matrix is always equal to the geometric multiplicity of every eigenvalue. Because, and this follows from the fact that symmetric matrices are diagonalizable, and we have a necessary and sufficient condition for a matrix to be diagonalizable. And that necessary and sufficient condition is that algebraic multiplicity of an eigenvalue equals its geometric multiplicity for all the eigenvalues. So here we have geometric multiplicity of lambda is equal to 1, and this means that hence algebraic multiplicity of lambda, sorry, not lambda, but this actually k here. So algebraic multiplicity of k is equal to 1. So this means the algebraic multiplicity of k is equal to 1, and they are actually equal. For a symmetric matrix, geometric multiplicity and algebraic multiplicity are equal. So as we know that the geometric multiplicity is equal to 1 for this k, therefore algebraic multiplicity of k as an eigenvalue is equal to 1 for a connected k regular graph. Now we will come to show that the modulus of each eigenvalue is less or equal to k. Okay, so the last step that we need to prove. So lastly, we prove mod of lambda is less or equal to k for every eigenvalue. For every eigenvalue of A. Now, let lambda be any eigenvalue of A. Let lambda be any eigenvalue of A and y equal to, suppose y1, so on, y and transpose be the corresponding eigenvector. Be the corresponding eigenvector. So then what we have, then we have ay is equal to lambda y. Also let yj be the entry in y with largest absolute value. With largest absolute value. And let aj denote the jth row of A. Then we have, so when we multiply the jth row, then aj, which is the jth row of A, when it is multiplied with y, we will get lambda times yj. So that is summation over I yi. This is equal to lambda times yg. Now again, as now this implies or this modulus of lambda times yj, this is equal to modulus of summation over I yi. But now this is a finite sum, so this is actually less or equal to, so this sum is less or equal to summation over I modulus of yi. But this yg is the entry with the maximum modulus, so this is less or equal to k times modulus of yj. So if we replace each of these yi's by yj, then this will be a bigger term. So this will be actually greater or equal to yj plus yj plus yj. So this k times yj. So that is, or this mod of lambda mod of yj is less or equal to k times modulus of yj. Now here, this yj is an entry in the eigenvector y with a maximum modulus. So clearly this yj has to be non-zero, because otherwise each entry of y is 0, and if each entry of y is 0, then y cannot be an eigenvector. So therefore this yj is a non-zero number, and modulus of yj is a non-zero positive number in fact. So therefore this equation clearly implies to us that lambda mod of lambda is less or equal to k. And this completely is approved. Thank you so much.